Hi everyone, thank you for joining Pacific Power Sources webinar. Today our presentation will cover the fundamentals of regenerative AC loads. My name is Julie Tran, and I am the marketing manager at Pacific Power Source, and I will be your moderator today. Before we get started, if you have questions during the presentation, please use the questions chat function located at the top bar. We'll have time to address them at the end of the session. When the webinar is over, please take a moment to fill out the survey that will pop up on the screen. I am very excited to introduce our speaker, Herman van Eikelenberg. He is the product director at Pacific Power Source and has over 30 years of experience in the test and measurement industry. He has held previous roles at Philips, Fluke, Danaher, California Instruments, and Ametek. He has an extensive background in engineering across design, applications, product development, and management with a heavy emphasis on AC power. He has a wealth of knowledge that we're really to tap into. And with that, Herman, I will pass it over to you.
Thank you, Julie. Welcome, everyone. Happy to be here and provide this presentation to you. The topic for today is electronic loads, but we cover a wide range of products as a global supplier of AC and DC test solutions. That includes both AC and DC electronic loads, as well as grid simulators, AC power sources, EM test systems, and associated software for control and automation. The webinar today consists of three sections. The first part will be fundamentals of AC loads, go over applications and use cases. We will cover the differences between resistive and programmable loads. We'll look at benefits of regeneration and the types of load operation modes. The second part consists of a couple of demonstrations of the actual use of the electronic load for a couple of different scenarios. So we'll be doing a demonstration for you with our products, and then I do a summary and look over some of the key criteria and features which are important when selecting electronic loads for your test applications. AC load applications, of course, are numerous. They involve a wide range of products that are operated from the power grid, run as such on AC power inputs. So applications include energy storage systems such as wind and solar with then battery backup systems, so that are connected to the grid. There are also distributed energy resources that are connecting to the grid, especially renewable resources that are used to provide power to the power grid from solar and wind resources. In the automotive space, electrification of vehicles requires charging systems and charging stations, both on the car as well as public charging stations. Those are typically connected to the grid as well, of course, for their power source. So they need to be tested as well. And then, of course, in the military and aerospace world, there's a lot of AC power applications on board and airborne systems that typically run at higher frequency than the public utility grid, but of course also need to be tested, and both AC sources and electronic loads are used there as well. And a big part of electronic load is life cycle and burn-in testing, which is needed for quality assurances and quality life testing, and other examples of products that are AC powered and connected to the grid are UPSs and power distribution unit systems. So quite a variety of products that are AC powered and require testing, which very often involves the use of loads. Here are some examples of distributed energy resources that are commonly used these days to supplement the power grid and try to move away from the use of fossil fuels. So they include solar and some other resources that are able to generate power and contribute to the power grid demands. AC loads come in different types and source formats. There are linear loads, which are typically made out of resistive components. You can also have a combination of capacitive and inductive components added to that. So as such, you create LCR load combinations. And those are considered linear as they will follow the voltage sine wave and produce a sinusoidal current. The use of capacitance and inductance will allow you to phase shift the voltage versus the current. But in general, the load sources, these kinds of loads are linear in nature. Nonlinear loads consist of other components, typically rectifiers and diodes, which will cause nonlinear load situations and current, and power factor corrected loads, which are aimed at reducing the power factor of the load conditions. So those are two ways to differentiate loads between linear and nonlinear. Another differentiation to make between loads is those that are resistive loads or resistive load banks versus programmable loads, which are generally electronic loads that can be changed in value. Resistive loads are very common. They've been around for the longest time. They're very simple in nature, but they don't offer a lot of flexibility. Loads, resistive loads are typically fixed, and setting adjustments is generally done through a series of switches or rewiring the load, which is not very convenient, not very flexible. They also produce, load conditions that are always a power factor of 1, so the voltage and current are always in phase because they're resistive in nature. So unless you add capacitance or inductance, you always have a 1.0 power factor with these kinds of loads. And in the real world, a lot of loads are not necessarily pure resistive. So they often have a power factor that's less than 1. And in this situation, you're not generally replicating real life conditions with such resistive loads. Another downside of resistive loads, of course, is they are not energy efficient in that they burn off all the energy into heat. So it's very energy inefficient to use resistive loads, especially for long-term burn-in applications where you're running the loads for very long periods of time to do product burn-in. So it also will require you to possibly upgrade your HVAC system to keep your facilities cool if the loads are inside the building. Very large resistive loads are often put outside for that reason, which means the distances between the EUT and the load is generally larger. Add some inductance as well, which you may not want. And applications for these are typically, primarily burn-in because they are simple in nature and relatively inexpensive to put into place. Sometimes for product development as well. Programmable loads, on the other hand, are more flexible. They are generally electronic in nature, so it allows you to change the load conditions more easily remotely or through programming capabilities. They come in two types as well. They're either dissipative loads, which are generally conventional electronic loads, or regenerative, which have the ability to recover most of the energy back to the grid. So on both of these types, programmable loads are generally easy to change settings. You can do it remotely. You can do it from the front panel. It's easy to dial in different load conditions because they're fully programmable. Power factors are generally adjustable as well, so you can vary your power factor anywhere from -1 to +1 on regenerative load. On dissipative load, you have less of a range. You can generally adjust power factor, but not over the full ±1 range because they are not bidirectional, so they can only be adjusted to a limited amount. If the load is regenerative, then you have additional energy efficiencies that you obtain as you can recover a large part of the energy that is absorbed by the load back to the utility. They both are programmable and therefore easy to automate your test systems with. And they can be smaller than comparable resistive loads, especially the regenerative loads that don't need large amounts of heat sinks to dissipate all that energy that you're burning off in a regular dissipative load. So regenerative loads have the additional advantage of smaller footprint and smaller to install. Applications for programmable electronic loads are very similar to resistive loads in a lot of ways. They are often used for burn-in, especially regenerative loads are very suitable for burn-in because of the power efficiency that you obtain. For product development, of course, you have a wider range of capabilities on an electronic load, so you can program a much greater number of load conditions to really test out and shake out your power source designs with it. And they offer more complex load conditions that you can simulate. So they're generally programmable, and you can do very sophisticated load transients that will really test your load or your product under test very thoroughly. So benefits of regenerative loads in particular are obviously in the area of energy savings. So in the case of a regenerative load, your power is basically converted back to the utility instead of being dissipated into heat. So that also means they have the ability to cover a wide power factor range from both plus and minus 1.0. So they can cover the entire programmable power factor range for your load conditions. One of the biggest advantages, of course, is the energy savings and thus the cost savings that you obtain. Typically, regenerative electronic loads have a ability to cycle about 90%, a little over 90% of the power back to the utility. So you're recouping a lot of energy by using regenerative loads. It also means the heat generation of load is considerably lower. You're not burning off all the power that you absorb from your unit or test into heat. So it also means your energy HVAC systems can run at a lower rate. They don't have to work as hard. That makes also for a more comfortable work environment for the operators, since you're not working in a hot environment. One of the advantages of regenerative loads is that they are 4-quadrant. So whereas regular conventional dissipative electronic loads have 2-quadrant operation and positive and negative voltage, but they can only absorb power, so the power flow is into the load. Regenerative loads are bidirectional, so they operate in 4 quadrants. So they're 4-quadrant loads, which means they can not only regenerate power back to the grid, but they can also shift the power factor or the phase angle between the voltage and current in both a positive and negative directions. So it allows you to have full programmability over your power factor of your load condition. So that's illustrated on the left where you see the 4 quadrants being used in case of different power factor settings. Regenerative AC loads to recycle the energy. So most of that power is going back onto the grid, saving you both cost and energy. So it's very suitable as a result for renewable energy system testing, which is often can be bidirectional as well. So simulating solar and wind, testing solar and wind inverters, grid-tied inverters, another example of energy storage systems, battery inverters. In this case, it would be AC as well. UPS interruptible power supplies can be tested easily that are connected to the grid and allow you to also do performance validation. Battery discharge testing is another application for DC load mode, and general power supply and AC DC or DC AC converter testing. So these are just some types of applications where regenerative electronic loads are a very suitable solution. Other examples, EV powertrain components, generally high power systems here. Aerospace and defense generally require higher frequencies than the grid frequencies. Very often 400 or up to 800 hertz are needed, some cases higher. So those are suitable candidates for electronic load test applications. And as well, motor drives, a good example of variable frequency drives or fixed frequency drives, motor test applications where AC power is used to generate momentum. Quality and safety tests in general, of course, of AC powered products, also suitable for doing life testing or for limit testing of your products. Looking at programmability of these loads, electronic loads generally, especially those that can do both AC and DC, have a number of load modes of operation that are typically available for the user. The most common type on the both AC and DC side is constant current mode. This is the most intuitive mode of operation. You basically determine how much current do I want to pull from my unit under test, and you basically dial in that current, either an AC current or a DC current, depending on the mode you're in. There are some variations on those modes, such as constant power, which is similar, except you're setting a fixed power level, so the voltage and current can both vary along a constant power curve. And another example of that is apparent power instead of true power. So you can both do this for either VA or for watt constant settings. And another variation of that again is the resistive mode, which is another way of thinking of setting a load. Would be similar to a resistive load bank where you don't set the current you want, but you basically set a resistor value setting. So as the voltage vary, the current will vary proportionally with that. And for some current sources, if you want to test current sources, you generally need a constant voltage mode, which is the opposite of a constant current mode. And many electronic loads will offer both. Similar on the DC side, so you have very similar types of load conditions there. On the AC side, there are some additional AC specific types, which can be combinations of CC and CR, or what we call rectifier modes, where you can simulate either a single phase or a three-phase rectifier type current pattern. So you don't have sinusoidal current, but you have rectified currents that you can use to load your unit under test. Having these modes available gives you a lot of flexibility and capabilities, and because it's programmable, it can be easily integrated into an automated test situation as well. So it makes for very suitable testing. Another mode that applies to AC mode in particular, AC loading, is the what we call circuit emulation mode. This is where you have a combination of resistive and inductive and capacitive elements that you can combine into different network topologies. In case of our AC load, we have 15 circuit topologies that you can select from of different circuits of L, R, and C components to simulate a wide range of linear circuits. That includes rectifier mode as well, so you can simulate rectified inputs and add an amount of capacitors and inductance to simulate different load condition. One example of this kind of operation would be PV inverter testing, where for the anti-islanding test requirements, you will need an LCR load combination connected to the PV inverter output. So to complete or perform that test according to the requirements. So that's a good example of using the circuit emulation mode. So with that summary or overview behind us, let's subsequently switch to a couple of demonstrations that we have put together using our AZX series products. All right, so before we get into the demos, I'm going to show you a quick summary or an overview here of the actual demo setup we're going to be using. We have two AZX products here. One will be used as a grid simulator, the one on the left, and on the right we have a same product, but it's set for electronic load mode, AC mode in this case. So we'll be loading down the grid simulator with the second AZX as an AC load. And we have both these units connected to our facility power. So they both are powered from the same grid feed. And we have a couple of APS M2000 power analyzers connected. One is connected to the grid connection, so we can see how much power flows into or out of our facility power to run this whole test setup. We have one connected at the output of the grid simulator and the input of the load, which will allow us to see how much power in what direction flows between the grid simulator and the load. And then we have a third one that's not shown here that actually looks at the input power of the electronic load on the right in particular, so we can see how much power from the grid flows in or out of our load. And in case of a load, generally, it'll flow out of it back into the utility. So we should see the power flowing out of the grid connection of the electronic load when it's under load. So that's the setup that we'll be using for this demonstration. We'll do a couple of examples of load modes that are very common. For one, the first demonstration we'll do will be one with the CC mode, where we do different load conditions using the current programming. We'll show you what that looks like. And then we'll run another example, a more sophisticated example of a rectified type load condition where we will simulate a typical inrush current that occurs when you turn on a load for the first time and the input rectifier capacitors are uncharged. So there will be a surge current that goes in initially that will then decay. And we'll show you how you can easily set up these kinds of load conditions on the electronic load using the circuit emulation mode. Before we start our application examples, let's take a look at the equipment setup we will be using. On the left, we have a 55 kilowatt AZX series regenerative grid simulator used to represent the unit under test. On the right is a second AZX set to AC load mode. The output of the grid simulator is connected to the input of the load. Both units can be operated from the front panel using the keyboard and color LCD display. Measurements are available as well to read back voltage, current, and power from the grid simulator as well as the load. The 19-inch cabinet contains 3 APS M2000 digital power analyzers. The top power analyzer is labeled test connection and displays the power flow from the grid simulator to the electronic load. At 277 volt, the load is pulling 45 amps per phase. That equals 12.465 kilowatt per phase, or 37.3 kilowatt total. The center power analyzer shows the grid input of the electronic load. It shows how much power the regenerative load returns to the power grid. Of the 37.3 kilowatt test power, 93% is returned to the grid. The bottom power analyzer is marked AC mains and monitors the power that flows from the facility grid to the test setup. Only 5.64 kilowatt of grid power is used to cover conversion losses of this entire test setup. Using this setup, we will now run through a couple of examples of the AC load operating mode. This first demo uses the circuit emulation load mode. We will use the Smart Source web browser interface of the grid simulator to have a better view of the AC source and AC load settings. In the first screen, we're showing the AC source settings. As you can see, the AC source is set to 3-phase voltage output at 60 Hz and 277 volts line to neutral, which is equivalent to 480 volts line to line. The AC source output is on. Let's switch to the electronic load browser window. The load is set to constant current mode, so we need to switch to the circuit emulation mode instead. Use the type field to switch modes from constant current to circuit emulation mode. Other load settings like the phase mode, AC solid voltage range, etc. remain the same. We are now in the CE mode where individual resistance, inductance, and capacitance parameter values can be programmed. Parameters for R, L, and C have already been set, and the current type selection is set to rectifier 3-phase. This setting will give us a 3-phase rectified nonlinear current waveform. We can now enable the load by clicking the On button. And the load is now enabled. And if you look towards the bottom of the screen, you will see the measurements readout. Power readings of all 3 phases show 6.6 kilowatts per phase, or 19.8 kilowatt total power for all phases combined. To view the current in the time domain, we're going to switch to the internal scope function of the load by selecting the measurement window. Here is the load's internal scope display. It's still showing the previous acquisition, which was in constant current mode. Press the Scope Capture Run button at the lower left-hand corner to run the scope. The voltage and current waveforms for all phases at the load input are now visible. To get a better view of single phase, we will turn off phases B and C. This provides a better view for a specific phase. That concludes our first example. Let's now look at a more complex AC load setting using constant current mode and the available transient capability of the AC load. Our next example of the programmable AC load involves the use of the transient capabilities. For this example, we will look at the inverse current transient functions. The power source is still set to 277 volts AC, line to neutral, or 480 volts line to line output as in our previous test, as you can see on the AC source control window. So let's switch to the load screen next. The load is still in circuit emulation mode, so we need to set it back to constant current mode as well to create a current transient. With the load back to CC mode, we set the current setting to 15 amps per phase. Apply the new setting and turn on the load. As you can see, the load currents for each phase are 15 amps, and the total power per phase is 4.15 kilowatts, or combined 12.45 kilowatts, as we can see in the highlighted green area. This is the amount of power that is being pushed back into the power grid. Next, we're going to select the transient mode from the control menu and set the transient system of the load to inrush execution mode. The inrush current value settings are on the right. The diagram below it illustrates the various available stages of an inrush current transient program. As we can see in the AC current set point, the steady state current of the load is set at 15 amps RMS. We're going to set the initial surge current level to 45 amps, or 3 times as high, and apply the settings. On the left hand of the screen, we see the inrush current timing parameter settings that allow the user to determine the nature of the current decay over time. These set values include repeat time, exponential delay factor, PFC simulation, turn-on time, ramp time, PFC current, and steady state time. The PFC emulation mode can be enabled or disabled by the user depending on whether he wants to use that mode or not. If the mode is enabled, of course, the PFC related settings below it will have to be set according to the requirements. Once set, we are ready to apply these parameters to the load transient system using the apply button at the bottom. But before we execute the inrush transient, we need to set the internal scope in order to capture this. So let's go to the scope screen. And the first thing we're going to do is adjust our horizontal time base to give us a longer acquisition window so we can see the entire event. So we're changing it to 50 milliseconds per division. So we get several cycles per division. And then we're going to next set the trigger mode to transient run. So it will trigger on the start of a transient execution, in this case, our inrush current transient. And of course, we can tell it to capture all 3 phases and all 3 voltage and currents, or just one phase. So right now, let's set it for 3 phases on the voltage and the current. We hit the run button and the scope is now armed and waiting for the transient execution to trigger it. So returning back to the transient screen, we can now hit the run button to start the inrush current transient. And you'll see the unit is programming itself and executing the transient. And it's completed. So let's go back to the scope screen. And here we see the 3-phase voltage and currents for the inrush current event that we just ran. To get a little better view, let's turn off phase A for phase B and C, and so we can focus on phase A. Might give us a little better view. So there's just phase A for the voltage and then of the currents for B and C. So now we can see both voltage and current for just phase A. And if we just want to see the current, we turn off the voltage as well. And here is our inrush current. As you can see, it's not power factor corrected initially. So as it runs through the inrush period, once the enriched period is over, it'll return to PFC corrected mode, which will be a regular sinusoidal current again. And at that point, we're in the PFC mode, and we're now simulating the steady state current of the load at the end of the transient run. So as you can see, with just a couple of settings and parameters and selections, we can create fairly complicated sequences of current in Rush using these built-in transient capabilities of the electronic load. And that concludes the last of our demos. Okay, so with these two quick demonstrations done, let's recap what we looked at here. Clearly, we were monitoring the power flow with the power analyzers to see how much power flows from the grid simulator into the electronic load, which the load is telling us as well in its measurement screen, and then how much of that power the load pushes back onto the grid. And as you could see on the demo, most of the power flows back into the utility grid. So, and since both the grid simulator and the electronic load were connected to the same power grid, we can see that the total power running these tests was a fraction of the actual power that's being absorbed by the electronic load and delivered by the grid simulator. So that's one of the big advantages of regenerative electronic loads, is that they don't really consume a lot of power. They recover the vast majority of the power that you're using to test back to the grid, saving you, in electricity cost. And especially if you're running long tests or burn-in tests at high power, that's going to add up to a substantial amount of savings over time, and we'll look at that later in the presentation. As for the examples themselves, we were using CC mode and CE mode in the different examples. The CC mode is, as I mentioned earlier, one of the most common modes, and it's also where it's very easy to do complicated current transients. Now, the example we used was a very complex sequence of events using both rectified current waveforms as well as PFC corrected sinusoidal type waveforms. And you can do that as part of the transient system like we did, or you can do similar things using the arbitrary waveform capabilities of the electronic load, which allow you to change your current wave shape to something other than a pure sine wave. So for the rectified modes, that is done for you, obviously, with either a single phase or a three-phase rectified current waveform. And you can tweak that as well to make it meet your requirements. Or you can create an arbitrary waveform and do the same thing there by switching waveforms as part of your load settings. So those are very powerful capabilities and make it very easy to come up with very complex load scenarios to really shake out and test your designs as far as your power source designs. Other functions that we haven't really looked at are also significant, but it would take too much time to go through all of them. What we also did, as you may have noticed, is we used our Smart Source Suite web browser interface because it gives us more screen real estate than the front panel would, and allows us to look at a lot more information at the same time, such as complex transient sequence lists that you want to study or edit and modify, as well as the built-in 6-channel scope capabilities that our electronic load has, that allow you to capture the events, especially transient events that are one-time events or short duration events, and subsequently trigger on that easily without having to deal with external test equipment or external scopes. Also very useful for ATE programs where you want to document the tests that you're doing by capturing some real-time captures of the currents and voltages that are being executed by the load and the grid simulator. So very powerful features that are all standard on our electronic load products. I mentioned already the power flow and the regeneration of power that is occurring in these kinds of test setups. So you're saving a significant amount of power, and as you do longer duration tests or higher power tests for both, those savings can start adding up considerably. So we have a little spreadsheet that we use to illustrate that here, where on the left you enter your typical usage information. So let's say you're doing some burn-in of a rack of products, and let's say you do that 5 working days a week in 8-hour shifts, or you can do 24-hour burn-in, obviously. But let's just say you do 8 hours, and so your total monthly hours is calculated there for you in yellow. And then you look at what is my total burn-in load. If it's 200 kilowatts, then and your local electricity rates are 30 cents per kilowatt hour, then this will calculate your effective savings in terms of using electronic regen loads versus resistive loads, which is the alternative. And then you can see have your total energy savings over time on the right. That if you have the 90% recovery, then you will save that much 3,200 kilowatts a month. And at the rate that you have 30 cents, that amounts to a total cost savings of $103,000 a year in this particular example. So that helps offset the cost difference between a resistive load bank and a regenerative electronic load bank over time fairly quickly. So the other additional savings that is not really calculated here is the potential savings on your HVAC costs. So not having heat generated by resistive loads will significantly reduce your air conditioning costs that you would have to incur if you want to keep a safe environment and for your operators to work in. So you would have to run your AC. That takes energy as well, and that takes a cost as well over time. So if you're interested, we'd be happy to share a copy of this kind of a spreadsheet with you so you can plug in your values and see what your scenarios cost savings would be in these situations. So they can be significant. Okay, we obviously only touched on the surface of the capabilities of some of these electronic loads. So there are more complicated things you can do. We didn't mention it, but you can not only use sinusoidal currents, but also harmonic currents as well as intraharmonic. So you can do immunity testing of your power supplies against these kinds of conditions. I mentioned that you have the ability to do custom waveforms as well, especially in CC mode. You can do other than sinusoidal wave shapes to simulate complex anomalies or disturbances that your power supply could be faced with and see how it responds to that, how quickly it recovers and regulates from that. And we'll do all this with the transient system, which we use the list mode, but there's also a step mode or a pulse mode transient system that is included. And finally, the Smart Source Suite web browser interface is very convenient to do complex tasks or operate or monitor the unit remotely. You use a tablet or a smartphone. Anything that runs a web browser can be used to connect to the load or to the other equipment that you may have to do remote monitoring and or documentation of what's happening in your test setup. So the message there is, of course, that smart control gives you more capabilities and makes things easier to use. So having the standard browser interface built into the product is a very convenient way to access and operate and program and save information. You can use it to run tests, execute tests, document tests, and we also offer pre-written test sequences for common test standards like inverter testing or IEC immunity testing for voltage dips and interruptions, etc. Those are predefined, pre-written, and you just install them on your load or on your grid simulator, your power source, and you can execute them, and it documents the test and generates a report at the end for documentation. Overall, having the ability to do everything under program control can help set up or speed up your test requirements, your test solutions using automated testing and computer control. So with these demos completed, let's summarize some of the load mode operation modes that we've seen used in the demos, as well as some additional loads that are supported by our electronic load. CC mode is the most common mode that's used, but variations of this like resistive mode or power watt VA modes are alternatives, and see what kind of power levels and voltage ranges the load needs to support to cover the products that you're testing. The CP mode, constant power mode, is similar to the current mode, except you're setting a fixed power level. So as the voltage changes, if you have variable voltage products, then the current will automatically adjust to maintain a fixed power level. And this applies to both mode as well as the CR mode. Constant resistor mode is another mode of operation where you set a resistor value. It's very similar to what you do on a resistive load bank. You have a resistor setting and the voltage and current track according to that ratio. So it's a fixed ratio between voltage and current. As the voltage goes up, your current goes up and vice versa. So typically used for component testing and some other types of test applications. Available as well. And we also looked at the crest factor capabilities when we ran the inrush current test, where we had a high crest factor current wave shape or rectified wave shape in this case, and that can be useful for stress testing your products, so your sources. So can they handle high peak currents? What kind of crest factor loads can they handle without this excessive voltage distortion, etc. So those are all possible examples of where you would use those kinds of operation modes. And then finally, CC mode, again, the most common mode that's generally used with, in this case, harmonics or interharmonics, where you use a non-sinusoidal waveform or a waveform that has additional higher frequency components in it and allows you to test your filter components and output stages of your power supplies. Another example that we mentioned is the CE mode, where you can set an R, L, and a C component on your load, so you can program the different linear components of your current. Very typical example for that is anti-islanding test of PV solar inverters. They will have to shut down if the power utility disappears for some reason. That has to happen within a certain amount of time. That testing is required to be met. And in order to do that, you have to disconnect the input power to the grid side of the inverter and connect it to at the same time to an RLC load that will simulate, typical load conditions on the grid that the inverter would see under those conditions. And it needs to be shutting off in a specified amount of time within a specified limit of time in order to meet compliance. So a typical example of where you would use the RLC mode of operation of an electronic load. Some of the test standards that apply to these kinds of inverters are listed below the 1741 and the 1547. Another feature that we offer on the electronic loads that we used here today is the PHIL, or the hardware in the loop interface option. This will allow you to run real-time simulations with a real-time simulator system. It applies to both our electronic loads as well as our AC sources and grid simulators. They all offer this HIL real-time interface, very commonly used for renewable energy microgrid simulation applications, where the hardware of the load or the power source is used to simulate real-time events using the simulator, and the signals are going into the unit in analog signals typically, and the unit provides back 6 readback signals for voltage and current, so the simulator system can monitor the reaction of the microgrid to the stimulus that is being applied. So very commonly used these days in high-end simulations of microgrids. So with that overview of the load capabilities behind us, let's take a look at some criteria and see what we need to select our units on. One of the criteria, of course, is regenerative capability, very efficient, energy savings for quadrant operation, so it operates in modes that non-regenerative loads cannot function, and it also has the ability to absorb back EMF from your units under test, which will put it back on the grid as well as the rest of the load. Modular and scalable is important. So can you grow over time if your needs change? Can you add additional loads to the one you have? By paralleling multiple units allows you to grow over time and start with what you need today and be ready for possible needs in the future. Flexible configurations, meaning can it do AC and DC, or can it do both? Do you have the ability to test both single phase, split phase, and three phase sources? And are you able to run the load into delta sources and not just Y sources. Um, in case of delta sources with no neutral, then you may need electronic load that has isolated neutrals instead of a common neutral for all phases, so which we offer on our electronic loads. IP current control, it can be important to test, stress test a unit under test. So that means you need a programmable crest factor capability for your current and allow you to replicate complex inverse current situations and conditions like the example we used today. Wide frequency range, do you need 50, 60 hertz plus minus, 3 hertz, or do you need higher frequency as well for avionics and defense applications? That may determine the kind of load you need. Can you do power factor shifting? Can you go full plus minus 1 on the power factor? Can you simulate the entire range? Generally, that requires regeneration capability. And then finally, does it have the ability to work with hardware in the loop systems as either an amplifier or a load, depending on your simulation needs. Finally, safety is important. So operator safety. So is the input of the load isolated from the grid connection, so you don't have any issues there. And can you operate the load, separately on individual channels if you want to do 3 different loads instead of one 3-phase load, which gives you additional flexibility in testing multiple units at the same time. And then finally, controllability. Is it easy to program? Is it easy to control? Do you have easy access both from the front panel as well as remote, which is one of the reasons we add the standard browser interface. In summary, this is an overview of the electronic loads that are regenerative that we offer. We have 2 model series, the RLS series on the left and the ELZ series on the right. Both are regenerative. They are different power levels. The unit on the left, the RLS series, is a rack mount unit. Takes up 4U or 7 inches of rack height. It's rack mountable, therefore, and comes in as little as 6 kilowatt all the way up to 21 kilowatt in that 4U format. So very high power density for electronic load. It can be paralleled to higher levels, so you can go up to 252 kilowatt by paralleling multiple units. Voltage ranges on this unit are 350 volts line to neutral, or over 600 volts line to line in the AC mode, and plus minus 500 volts in the DC mode. And the operating frequency is from 15 to 1200 hertz, so it covers both, commercial products as well as avionics and defense products. The ELZ is a cabinet system, so it's its own rack. It comes as small as 30 kilowatts and up to 55 kilowatts in one rack, or you can parallel up to about 440 kilowatts by having multiple units in parallel. Voltage ranges are a little higher on this unit. There's dual range. You have either 225 on the low range or 450 volts line to neutral on the high range. On the DC side, it's plus minus 600 volts DC, and the frequency range is 15 hertz to 1000 hertz. This ELZ series model also has the HIL hardware in the loop option available to it. So these are the 2 load products that we have on the regenerative side. We also have some conventional electronic loads that are non-regenerative. So these are what we call dissipative electronic loads. They come in both DC loads as well as AC loads. It's a whole range of programmable products. They are very capable in terms of load modes, but they are dissipative. So you will be dissipating power, and at high power levels, they tend to be a little larger because of the size of the heat sinks required to do that. But if you're interested, then contact us about non-regenerative loads as well. And finally, we have regenerative grid simulators or AC sources as well. On the left, you see the RGS series, which is our rack mount unit. It's also a 4U unit, same power level, 21 kilowatts in this one unit. Voltage ranges are the same as the electronic load, so 350 volts AC line to neutral, or 606 volts line to line. And on the right, you have the GSZ series, which is same format as the ELZ electronic load we just saw, 55 kilowatt per chassis, per cabinet, if you will, and same voltage ranges, 225 and 440 as the electronic load. Also, both have DC capability as well. So these are the two different products that are available, and many of the features that you've seen are available on both product lines. So in summary, Pacific Power Source has been in this electronic power business for over 50 years. So we have a long-standing reputation for high performance and reliability and best-in-class user experience. Our products are scalable and versatile and meant for growth, and we can help customize and modify units for specific requirements if needed. Generally deliver standard products quickly and have a wide depth of application expertise built up over the last 50 years, as well as excellent customer service and support for any of your AC power and DC power testing needs. If you need to get in touch with us, here's some contact information. You can reach us online at pacificpower.com, or you can call our offices. We have facilities in the United States, Asia, as well as Europe, where we have customer service and support facilities, as well as sales and application support.
Okay, thank you so much, Herman, for that informative presentation. We are now going to open it up for any questions. Oh, sorry about that. Okay, I see some questions here, Herman. The first is, how can the loads be used on the grid without a generator?
Well, the load, we were using a grid simulator in our demo setup because it gives us ability to control the voltage and frequency that goes into the load because it's all programmable. But if you have an electronic load and you connect it to the grid, then you obviously can, which is a source as well. It's just not programmable. It's fixed. Obviously, the utility controls it. But you can use the electronic load to load down the grid. I'm not sure what you would do that for, other than maybe testing some equipment that you have in between, or some switching gear that you have connected to it. But any AC source or DC supply, for that matter, that you have can be loaded down with the programmable load in either AC or DC mode, depending on what kind of source it is. So for our purposes, we use our AC source or grid simulators because it gives us control over that side as well. We demonstrate the electronic load, but you could have a grid connection and hook the load up to that, and then of course it would be a fixed. In the US, it would probably be 280 volts or 480 volts three phase, or a single phase 230 volts or 120 volts, and then connect that to one or three phase electronic load and load it up that way. So as long as it's a voltage source and you put the load into current or power mode, you can do program what you want on the load side and draw whatever current and power you'd like to draw out of that supply that you're using to test.
Okay, perfect. And what safety mechanisms are in place for the web browser control to prevent any damage?
Yeah, that's a good thing. I mean, good question. Just the browser potentially allows you to operate remotely if you want. It doesn't have to be right where the equipment is, and that can be risky if you don't know what's connected to it. So there are a number of layers of protection that you can set on the browser function on the power on the load. You can set it to read-only mode where you can only use it to monitor. So if you wanted to see the measurements or the scope function displayed, and you could do that remotely on the web browser or on your tablet or on your phone, but you couldn't control anything, so you have no ability to change any settings or turn the output on or off, or it would just be monitoring only. That's one layer of protection. You can also lock it out completely, saying, I don't want anybody to use the web browser. I just want you to only operate it from the front panel, or I want you to only operate from our test program that we've written and that is controlled some other means, through another device or whatever that is, PLC. So there's different approaches there. So it really depends on your setup and who's going to be using it. So generally, when you're developing test programs or test sequences, the developers and the engineers that do that would have to have access to control the output and or the load settings to determine what is the correct way to test their EUT. And then once that has been defined and documented and programmed, then you can have other people using those programs that are already debugged and written, and then they can't make any changes to that and then just execute it. So to perform the actual test or to perform the burn-ins that they're supposed to do in production or test. So again, it depends on your situation, what makes the most sense, and what level of access you wanna allow on the equipment that you have. So it's completely up to the owner of the equipment to determine what kind of access level he feels is appropriate for them.
Okay, thank you. And this one question is about getting the possibility of getting a demo or recording of a load with harmonic mode. And I think to respond to that, we can definitely work with any of you who has a specific project or you're looking for something specific with our team, and they can get on a call with you, understand your project better, and then show you a very specific example for the demo so that it's relevant to your project. So please reach out to us. We'll follow up with you as well. And let's see here. Okay. Someone is asking if the AFX meets the same test standards as the RLS ELB series.
What was that first acronym you used? Was it
Uh,
AZX or
the AFX, which is
AFX?
for yeah, one of our power sources. For those who don't
Yeah.
know.
Okay. Now the AFX series is a programmable AC and DC power source supply. So it's not doesn't have an electronic load capability available to it. It's a unidirectional product, so it's not bidirectional. So it will take grid input power and then put out whatever AC and DC power you want on the output to run any loads that you have, depending on whether AC and or DC. But it's a unidirectional, standard, conventional programmable AC source. So it therefore does not have any load capability because that requires that you get rid of that power somehow, and that would require a bidirectional product like the AGX or the GSZ. So that we used for this demonstration. So we do have rack mount versions of the AFX products that are called, AGX series that are similar in size, but are bidirectional and therefore have the ability to be used as an electronic load as well. So
Perfect. And what is the downside on using a regenerative versus a non-regenerative load?
the downside, well, they tend to be a little more expensive for the same power level typically because of the bidirectional nature. So generally, the acquisition cost can be a little higher than a conventional dissipative load. But generally, the cost savings and energy recovery tend to nullify that over a relatively short period of time. So when you look at the total cost of ownership, it generally, especially at higher power levels, if you're doing a few, at 1 kilowatt, it might not add up that quickly. But if you're testing 5, 10, 20, 30, 100 kilowatt products, then those energy savings, especially if you're in an expensive state like we are in California, it's it's going to nullify that acquisition cost difference pretty quickly over time as you use the products. So that's really the main difference is just the acquisition cost can be a little higher because it's a more sophisticated design and it has more design content in it, and therefore it tends to be a little more acquisition cost higher. But again, all in all, I think if you look at the long term, you might find that it's actually more cost effective than a conventional load.
Thank you. And I think we have time for one more question. How do I create a custom current waveform?
There's a couple of different ways. First of all, it comes with a library of about 16 typically used non-sinusoidal waveforms that is built in, so you can select one of those. There is you can use a spreadsheet to download a custom waveform. There's also in the browser function, there is a waveform editor function screen that allows you to generate, for example, by selecting a number of harmonics and then summing those together into a harmonic waveform, or other functions that you can call up to create your own waveform, or you can, as I mentioned, create a custom waveform using that editor or using a spreadsheet, and then download it to the power source or the grid or the electronic load, it holds about 200 user waveforms at a time. So you can basically save those in no volatile memory in the unit, and then you can select it from the screen or from the front panel or the browser to pick the waveforms you've created in the past and select the one you want to use at the output or at the current wave shape of the load.
Okay, thank you so much, Herman. Thank you, everyone. We will be sending out the presentation as well as the recording. And if you have any projects or need project consultation, please contact us. And we look forward to seeing you at the next webinar. You can check back at our website for any upcoming events. Thank you all so much. Have a great day. Thank you, Herman.
You're welcome. Thanks, everyone.